We'll continue to look at volume by slicing, but now let's look at a cone. So we want to use slicing to find the volume of a right cone with height 10 and base radius 5. So picture something like this. And just like we did in the previous shapes, let's consider that we'll use horizontal slices. And again, we can think about just choosing an arbitrary slice to make sure it's clear what that looks like. So I'm chopping this up horizontally. We can see that this very small height here is delta H. And again, we're going to start to think about how we can construct an appropriate formula for the volume of a general slice. So much like we saw with the hemisphere example, if I'm going to consider what that slice looks like shape-wise, it is almost a cylinder. So almost in the sense that, again, the base circle is going to be slightly larger than the one on the top. But like we've already established, I can make a choice of a particular radius value. And for instance, I could choose this top one and force a cylinder onto that, where the idea is that that volume will almost be equal to the volume of the slice there. As I send the number of pieces to infinity, then we'll get a definite interval that will give us the exact volume, and so we won't have to worry about which radius, which height we focused on in that example. Okay, so we have an almost cylinder. Now I'm going to go through my steps that we established before. Again, h sub k says take the interval of height values, which has, this is length 10 here, divide by the total number of slices n. That's not the right notation. That's delta h here, not h sub k. So delta h is 10 over n. H sub k is, again, the smallest height value, 0, when we're at the floor, plus k delta h, which is going to give me 10k over n. And then the volume of my kth slice, because I'm fitting it with a cylinder, is again pi times the radius of my kth slice squared times that height delta h. So just as we did in the previous example, we now run into a problem that my integration variable is h, and I have my volume formula here represented as dependent on r. And same as we saw before with the hemisphere, certainly as I move h upward, I have the situation that the associated r value is going to get smaller. Those circles that we see decrease in radius as we move up the cone. So we want to establish that relationship between hk and rk. I'll point out what we're going to see is it's not the same relationship we found with the hemisphere. So it very much matters what's kind of behaving as the bounding relationship here in our shape. So with the hemisphere, what we did is we thought of a two-dimensional view of the hemisphere, and we got a semicircle. So if I follow that same strategy here, if we think about this cone and imagine looking at it from the front, we wouldn't get a semicircle, but we would get instead a triangle. So this would be kind of the two-dimensional view that we have there. Now, we know certain aspects of this triangle. I know that, if this is my slice, well, r sub k refers to this distance, so from here to here, just halfway. And h sub k would be the distance from the ground up to our slice. We want to establish a formula that relates those two. What I want to pay attention to is the fact that I've dropped kind of a perpendicular here. So what I can take advantage of here is not Pythagorean theorem, but instead similar triangles. Now, what we can look at is I have really two right angles here, but what I want to think about is trying to set up a relationship here where I'm going to look at my small triangle here and the larger triangle it sits inside. Those two triangles are similar. Now the larger triangle we can think about has height 10, and that base of this larger triangle is exactly the radius of the cone, the base radius, and we said that was 5. So that's coming from these original dimensions that we've drawn in this picture here. That should be similar to the height of, and so let me try to make this clearer. The height here divided by this dimension. So that's what I'm looking at on the right hand side here. So that height, be careful, that's not h sub k. Notice that that blue height is 10, the total height, minus the height h sub k, which is that distance down there. And then the other dimension we're comparing here, if I stop moving this, is what we're calling r sub k. So by using similar triangles, we set up this relationship. I would like to be able to replace r sub k. So we know that this is 2. So we see that multiplying both sides by r sub k, I get 2r sub k is equal to 10 minus h sub k. And then r sub k would then be 10 minus h sub k all over 2. So that tells me how I can replace r sub k. I'll point out another way we could get this relationship is if you were to think about this triangle sitting on your xy axis, then to think of r sub k is kind of like your x variable and h sub k is like your y variable. Well, when we're finding this relationship between them, it's the same thing as trying to establish the line equation that this illustrates here. So that would be another way, right? We know that we could find the slope and a point that passes through. So either way, but we should establish that we get this same formula that relates r sub k and h sub k. So with that, I can say that v sub k that we found above is also equal to pi times the quantity 10 minus hk over 2 all squared delta h. When I want to find the approximate volume, I can do so by summing the volume of my n slices, and that looks like the sum from k equals 1 to n of pi times the quantity 10 minus h sub k over 2 squared delta h. And from that, we can say that the volume is equal to the limit as n approaches infinity of the sum from k equals 1 to n of pi times the quantity 10 minus hk over 2 all squared delta h. And this defines a definite integral, and we know that delta h becomes dh. My integrand becomes now then pi times the quantity 10 minus h all over 2 squared. Again, I don't want to have the k in there. And to find the bounds of my integral, I need to go back up to the context and think about the appropriate bounds on the height. And I see here that at the base of the cone, the height would be 0, and the furthest point away we know is going to be 10. So this integral should give me the exact value of my volume. Let's see if I can add another page. So now we just want to evaluate this. Here we're going to have, so squaring the 1/2, I can bring out a 4. And then what's left on the inside is, so actually let me write, so bringing out the 4, so then we have, what's left here would be 100 minus 20h plus h squared. So in evaluating this, I have my multiplier, pi over 4. Then the antiderivative here is 100h minus 10h squared plus h cubed over 3. And we're evaluating this from 0 to 10. So plugging in 0 is going to give us 0, so I can focus on the 10. So we get pi over 4. 100 times 10 is 1,000. And 10 times 10 squared is also 1,000. And we're left with 1,000 over 3. And so these 1,000s cancel. And what we're left with is we can say that 1,000 over 4 is 250. So this yields 250 pi divided by 3. So again, the theme kind of with all three of these examples is, again, this process of constructing the appropriate Riemann sum. So we get to a point where we know exactly what that integral should look like. And a key step along the way is making sure that we can relate the two variables that are involved here, because we don't have a constant integrand.